In this video, we'll be learning how to use a tree diagram to solve a problem in probabilities. Now in this case, we're told that we're given a biased coin for which the probability of obtaining heads when we flip the coin is equal to 0.3. And we are asked, what is the probability of obtaining exactly one head when we flip the coin twice? Now the first thing to note here when we are dealing with this kind of problem is that the outcome of each and every single flip of the coin is completely independent of the previous or the next flip. What we mean when we say independent is that, for example, if on the first flip we obtain tails, this will in no way have an impact on the outcome of the second flip. That's what we mean by independent events. So each flip is independent. The second thing we note is that since the probability of obtaining heads is equal to 0.3, and since there are only two possible outcomes, heads or tails, this must mean that the probability of obtaining tails has to equal to 0.7. And the reason for this is because the sum of all the possible probabilities has to add up to 1. And so in this case, the probability of obtaining heads plus the probability of obtaining tails has to add up to 1. So, let's get started. The way we're going to draw this tree diagram is explained here. We have our starting point before we flip the coin. And when we first flip the coin, in other words, the first flip, there are two possible outcomes. We can obtain either heads or tails. And we draw these two possible outcomes as follows. We draw the first branch here, at the end of which we write H for heads. That's one possible outcome of the first flip. And there's a second possible outcome, which is tails. So we draw a second branch directly below that, and we label that T at the end. The next thing we have to add to this tree diagram is the probability of each of these possible outcomes. So we saw that the probability of flipping heads was 0.3. So we write that along the branch leading the starting point to H. In a similar way, we saw that the probability of obtaining tails was 0.7. So again, we write that probability on the branch linking the starting point to the outcome tails. Now on the second flip, again, there are going to be two possible outcomes. So let's say for a second that at the first flip we obtained heads. So we started here, we flipped heads, and so we're now standing here. The two possible outcomes on the second flip are again heads or tails. So we're going to add those two extra branches. Either we obtain heads or we obtain tails. And once again, we have to write the probability of each of those two possible outcomes along the branches. So the probability of flipping heads on the second flip is 0.3, and the probability of obtaining tails would be 0.7. If, on the other hand, on the first flip, instead of rolling, or flipping, I should say, heads, we flipped tails, so we'd be there. Then once again, there are two possible outcomes for the second flip, which would be heads, or we could flip tails. And just as we did before, we're going to write the probabilities of each of these possible outcomes along the branches. Now we're almost done. To complete this tree diagram, we write the overall outcomes on the right-hand side of the tree diagram. What I mean by this is, if in this experiment we flipped heads followed by heads, then the overall outcome would be heads and heads. Similarly, if we had obtained heads followed by tails, the outcome would be heads and tails. And we can carry on this way. Had we flipped in the first flip tails followed by heads on the second flip, that would have been tails and heads. And last but not least, the last possible outcome of this experiment could be tails on the first flip and tails on the second flip. So we write tails and tails. And the final step in completing this tree diagram is to write the probability of each of those outcomes on the right-hand side here. And the way we do this is quite simple. To find the probability for heads and heads, all we have to do is multiply the probabilities that we see along the branches as we go through the path. What I mean by this is we're starting here, and to get heads followed by heads, we have to walk up here, so that's 0.3, we obtain heads, times 0.3 again to obtain heads. So the probability of getting heads followed by heads is 0.3 times 0.3. And 0.3 times 0.3, you can check, is equal to 0.09. In exactly the same way, we now calculate the probability of heads and tails. To calculate that, we follow the tree diagram along the corresponding path. There will be heads on the first flip, followed by tails on the second flip. And the probabilities that we'd be multiplying would be 0.3 times 0.7. And again, you can check with your calculator, 0.3 times 0.7 is equal to 0.21. The third possible outcome would be tails followed by heads, which we see here written in blue, tails and heads. And the probabilities that we'd multiply in this case would be 0.7 times 0.3. And 0.7 times 0.3 is again 0.21. Last but not least, the final possible outcome is tails and tails, which we have here. And so in this case, we'd be multiplying the probability of tails, 0.7, times the probability of tails, which is 0.7 again. And 0.7 times 0.7 is 0.49. Our tree diagram is now complete, and we can now use this as a real tool in our problem. We were asked at the beginning to find the probability of obtaining exactly one head when flipping the coin twice. And the way we do this is we look for the outcomes here of this experiment in which there is only one head. And after a couple of seconds, really, we can see that the only two outcomes that we have here written in blue, which only have one head, are heads and tails or tails and heads. And I'll just circle those in orange here. We mean either this outcome or this outcome. Both of those only have one head inside in the outcome. And you may have heard this term before. Each of these possible outcomes is mutually exclusive. What that means is, to find the probability of this outcome or this outcome occurring, all we have to do is add their probabilities. So the probability of obtaining heads, or I should say, the probability of obtaining exactly one head, is equal to the probability of heads and tails plus the probability of tails and heads. So that's equal to 0.21 plus 0.21, which is equal to 0.42. If we wanted to write that as a percentage, we could write probability of exactly one head is equal to 42%. And there we have it. We've just used our tree diagram to calculate the probability of obtaining exactly one head for this biased coin.